So this session for ICSE class 10 revision on electromagnetic induction. So for ICSE class 10, you have in your syllabus, Faraday's law of electromagnetic inductions. Okay. So what you are having the these parts like what is electromagnetic induction and what you understand. Then what is the law of Faraday's law of electromagnetic inductions. Then there is an right hand rule for this one to understand the induced EMF and Lenz law, right? What is Lenz law? So this is all about and its application. So application part, you are having two things like one is the alternating current and another one is the transformer. Okay, so this is all about the class 10 syllabus, and definitely I'll help you to understand all this part, right? And this is about the Fleming's right hand rule. Okay, so this one, Fleming right hand rule. Okay, this is all about. So let's first understand what is electromagnetic induction, and before that, what is flux. So first of all, let's say this is a magnet. So this magnet, this is a north pole, this is a south pole. So what happened that the magnetic field lines will be coming out of this magnet, right? So these field lines will starting from here, north pole, and will close at the south pole. So it's a closed loop, right? It's an imaginary line which are magnetic field lines are coming out of the north pole, okay, and entering in the south pole. So these field lines, the next name is magnetic flux. So magnetic flux is the magnetic field lines, number of field lines which is crossing a particular area normally. So if you see here, okay, let me take it a bit closer. Yeah. So this is the magnetic field lines. The B vector, B is denoting the magnetic field. Okay. So magnetic field lines crossing an area A, normally. So this cause the magnetic flux. So flux denoted by phi. So flux phi is equal to B dot A, or we can say B a cos theta. So it's a scalar quantity. It's a scalar quantity. So magnetic flux is basically a measurement of the magnetic field lines. Okay. So this you understand. Now these field lines, whenever for electromagnetic induction, we will take a magnet and we will take a conducting wire in a coil shape or in a solenoid shape. Okay. Now we'll take this magnet very closer to the coil, right? Let's say this is a magnet and it will go very closer to a coil, and what happen, this coil will expose by the magnetic field lines. Okay, magnetic field lines. And whenever there is a relative motion, relative motion between the the conductor and the magnet, right? So there will be a change in flux. So let's say it is a conductor and magnetic field lines are getting exposed. It's a north pole, south pole. So field lines are exposed like magnetic flux are exposed on this conducting wire. So we have to change the exposure of the flux on this conducting wire. By how we can change, there are different options, like if we can make a relative motion between the magnetic flux and the conducting wire. Relative motion means I can take them closer, or I can make the conducting wire fixed. I can make a rapid motion of the magnet toward the conducting wire. I can take away the magnet away from the conducting wire in both the cases, and I can take away the conducting wire from the magnet. So in all cases we are making an relative motion between the magnet and the conducting wire. Whenever there is relative motion, so EMF will be induced. There will be induced EMF. So induced EMF caused by change in magnetic flux exposure on the conducting wire. This is about the electromagnetic induction. That means we are getting the electromotive force without using any electrical sources by changing only the magnetic flux or magnetic field lines. So this is about the electromagnetic induction. Okay. Now what are the factors like current flows? So like direction reverse, like electromagnetic induction causes flow of current in the conducting wire. Whenever there is a change in flux, so if you have a galvanometer here, okay, you will get a deflection in the galvanometer. That means whenever there is a change in flux, the conducting wire will passing some current. So current will flow in the wire. Next is the this flow of current, the direction will be reversed if we change the polarity of the magnet. So if we change the magnetic orientation during the exposure, the direction of the current will be also change. Okay. Now we can make strong magnet. So we can use, if you strong magnet, then the we will get the more current, right? And what are the things depends on it, like area of the coil, number of coil. Okay, that means what are the coil you are using for this case, that's very important for producing the amount of current. So coil normally we are taking like helical coil or like solenoid shape, right? In this coil, okay, if this coil is getting exposed through a magnet, it's a north pole and south pole. So this exposure happen. So number of turn of the coil, that is, if the turn is increasing means there will be more current. EMF will be more. Okay, and also the area of the coil increase, that is also causing the more EMF. Okay, so now what is the formula of the EMF? It is that is EMF is, this is a symbol minus N phi 2 by phi 1, right? This is phi 2 by minus phi 1 by T. That means phi 2 and phi 1 are the magnetic flux. So phi 2 minus phi 1 is the change in magnetic flux. Let's say initial flux on the conductor was phi 1, so it goes to phi 2. So change in flux will be phi 2 minus phi 1 with respect to some time. So rate of change of flux is producing the rate of change of flux is the induced EMF. Now what is N? N is the number of turns. So by increasing the number of turns, you can increase the amount of EMF. Okay. So if it's a single turn, then you will be writing EMF is equal to phi 2 minus phi 1 by T. Okay, this is the induced EMF. Now, what is why this symbol minus here? Minus here because there is an the Lenz law. Lenz law is saying that the direction of current will oppose the the cause for which it's producing. Like the current direction will always oppose the change in flux. So due to that reason, minus sign is here. Okay. So now let me make it more clear. The Lenz law. Suppose we are having a magnet here. This is north pole, this is south pole, and we are having a conducting wire coil, right? So if the north pole is approaching toward the coil, so here what happened? The north pole will be produced in this temporary magnet. Okay, here the north pole will be produced here, so that there will be a repulsion. So north pole repulsion happen. Okay, and again this magnet is going out away from this direction. Then what happen? The south pole will be produced here, so that there will be attraction. Okay. So in both the case, we can see that change in flux is opposed by this event. Okay. Now Lenz law also supporting the conservation of energy. Whenever we are approaching this magnet toward the coil, if there is a repulsion, then we have to do some work done, and this work will be converted into electrical energy by generating the EMF, induced EMF. So induced EMF is equivalent to the work done. So it's a Lenz law actually favoring the conservation of energy. Okay. So I think these are the things, and the last part is the the Fleming's right hand rule. So like if you take the right hand like this, and this thumb will be denoted the motion of the conducting wire, right? The relative motion, and this this forefinger will be the direction of the magnetic field. Then this this middle finger, right? Central finger will be denoting the induced current. So this central finger will showing you the induced current. So this thumb, again I am saying you, thumb is the direction of the conducting wire, right? Thumb is the direction of the conducting wire, motion of the conductor, right? And this forefinger is the direction of the magnetic field, then this, this particular finger, the central finger will be the induced EMF. Induced EMF. So this way, so this is the Fleming's right hand rule to know the relative directions, and this part, if you practice multiple time, it will be helpful for you to understand, right? So this is all about the electromagnetic induction basics, and the next session I will explain you the mechanism of alternating, AC generator, alternating current, how AC generator works with this principle, and also the transformer, how transformer works. Okay, thank you. Okay, bye.